All right. We have a very calm angel baby sitting in my lap. We hope she stays this calm. I make no promises. She just ate lunch. We're going to finish out the atmosphere module by talking about how this pertains to weather. So the topics we're going to cover are weather versus climate. We're going to define weather, movement of air, global atmosphere, and how that contributes to calm weather and heavy weather. No, Henry, don't do it. We're going to look at cyclones and hurricanes, atmospheric rivers, and then finally we're going to end on El Nino and La Nina. So here's some new vocabulary for you to consider. So I want to start, I always like starting this topic by discussing the difference between weather and climate, because these two words are thrown around a lot, right? When thinking about the atmosphere. And they're very different. But I think a lot of people think, oh, local climate, local weather, and they mean the same thing. So let's differentiate them to assess why we're learning about weather now and why I have a whole module later. It's the last module for climate. So weather, this is a beautiful depiction of fog on a stream system. Weather is the state of the atmosphere at a very particular, specific, and well-defined point in space and time. So it is a specific geographic location at a specific time. It is generally short term, so weather is indicative of minutes to days. And weather forecasts have little statistical value beyond roughly 5 to 10 days. So if you've ever checked the weather forecast, I've had to do it recently because I work out on a boat. And you're looking 10 days in advance and you're like, oh gosh, it's going to rain next Thursday. What you'll probably know to think, especially in the Pacific Northwest, is okay, well, I'll check back later because the forecast might change. Weather changes regularly. So don't get mad at your poor weather forecaster, your poor weatherman. He's doing his best. They're doing their best. And it can be very difficult to predict weather. It is non-linear and chaotic, but still predictable behavior that is associated with the physical evolution of the initial conditions into the future conditions. Versus climate. So climate is long-term. We have modeled climate for the next few decades, if not centuries. It involves components of all Earth's system other than just the atmosphere. So the climate, this is why we're doing all of these spheres, all the different spheres of Earth systems, because it all leads into climate. It is expected, it is repeatable, and it responds predictably to a forcing, which we'll learn when we talk about climate in a few weeks. It is generally predictable on long timescales from decades to centuries, but it's also predictable along huge spatial scales. So we understand climate more as a global scenario versus weather, which is very regional, which is very specific to a geographic location. We can think about climate as a global situation, a global scale. So weather can be defined or considered with 7 different terms. The first is environmental lapse rate. So I talked about this in the last lecture, but as you go up a mountain, it's going to get colder. And this has to do with the heat of the Earth's surface sort of being emitted from Earth's surface. So it's warmer at the base of, sorry, it's warmer at Earth's surface than as you go up. The change of this temperature is the environmental lapse rate, and it's actually at a very standard number. So the decrease of temperature is about 6.5 degrees Celsius for every 1,000 meters of elevation. So it's a standard rate. This is the environmental lapse rate. The temperature inversion is in certain circumstances, there is warmer air at higher elevations, and this is called, or this is known as a temperature inversion. This generally exists because of convection and because we have both vertical movement of air and horizontal movement of air. So every so often you reach a point where like, wow, it's warmer up in this elevation than it should be. And that has to do with the way that that particular geographic location is circulating air. This inversion always generates calm weather. The third term is adiabatic temperature change. So we're kind of going back to the sense to the concept, Henry, just sit. That lower atmosphere warms because Earth's surface releases heat energy, and as air rises and falls through the atmosphere, it experiences temperature change without necessarily adding or subtracting heat energy. Again, we're coming back to convection, right? Temperatures might change because of convection and because of the movement of horizontal and vertical air. We also see heat is being generated by compression, cooling caused by expansion. If you've taken chemistry before, this is all about the ideal gas law. No, I'm not going to dive into it. Just understand the adiabatic temperature change is not necessarily the addition or subtraction of heat, but the change in which the air is moving, the rise and fall, the movement from shifting from left to right. A parcel of air is when a meteorologist describes how air behaves, they use an imaginary parcel of air, like a balloon, a very thin elastic one, so thin it doesn't exist, but it helps sort of visualize this existence of a parcel, or if this parcel of air meets another parcel of air, because we see weather forming when two different parcels or balloons of air interact. The stability of a parcel is a parcels of air's tendency to rise or fall. So stable air will fall if it is not forced upward, and unstable air will have the tendency to keep rising. Air mass is similar to a parcel of air, but an air mass is small. So when we think about, and I know it seems backwards, at least in my brain, I'm like, air mass should be big, and parcel should be small. But air mass is on a regional scale. Air masses are defined by the region of origin, the temperature, and the local humidity. So typical winter weather in the Pacific Northwest is cold and wet. So the air mass delivers, I don't know why these have questions in them. I don't want them to have questions. We'll come back to these questions because I answered them all throughout the slides. But and then fronts. Basically, when two air masses interact, they form a front. And this is depending upon the air temperature and the nature of the moving air mass. So we might see a warm front or a cold front, and we're going to talk about those here in a second. And we can't necessarily see these masses interacting, right? It's not a visual thing. It's air. It's all invisible. But we find evidence of it through different weather and meteorological events. So the movement of air, when we see warm air advancing over cold air, we know that cold air is more dense. Anything that's cold is going to be more dense. This is a concept that we have driven into you with geosphere, with hydrosphere. Cold, dense water sinks. Hot, buoyant magma rises to Earth's surface. It is the same concept with air. So a parcel of warm air or a warm air mass can shift over cold air. And this is what we call a warm front, where the warm air is coming up to a cold air, and the warm air goes up. This causes very calm weather. When we see a cold front, this is when we see cold front advancing over warmer air, and we see heavier weather. Here we see a lot of rain in this capacity. And this is because cold air is more dense than warm air. So when warm air mass meets a cold air mass, the cold air ends up below the warm air. Once the air has risen, so the warm air has risen, it cools and clouds can form. So this is a depiction of a warm front where warm is sort of sliding up this cold air front. I do like these depictions a little bit better than these ones. These ones are a little funky, but this one shows, okay, we have warm air and it's going to rise. I shouldn't say, I was about to say float, and I was like, that's not right. It's going to rise above this cold air. And we see clouds, and we see rain. This is happening here too, and I apologize. We see rain in both of these scenarios, but we're going to get, the further we get into the coldness, the more calm weather we see. But when the initial hit hits, we see rain. So the structure of a warm front is pictured below. The warm air is forced to gradually rise above the cold air. And in the same concept of like a rain shadow, because we're forcing these parcels of air upwards, the water within that parcel is going to condense. And as it condenses, it turns to liquid. This is a cold front hitting a warm parcel of air. So the structure of a cold front is pictured above. Notice that the cold air is advancing. So this cold air is moving and it hits the warm front. And that warm front, or sorry, the warm air, the warm parcel gets hit and it's forced to rise very quickly. This is a nice slow depiction, right? When warm reaches cold, it's going to slowly rise above the cold. This is a very rapid and fast strike. So when you're like, oh, a cold front is coming, no, we're going to get a lot of rain because that cold front is going to hit the warm parcel and it's going to force that warm parcel up, and all of this water that was in this atmosphere is going to condense and rain on out. So this is going to give us showery precipitation. Now, this isn't necessarily a storm. It's just like, oh, we got a cold front. A little bit of cold air came in, pushed the warm air up, and it produced some rain. We also might have a stationary front where neither are really moving, or maybe they're moving at an equal rate towards each other. Neither, in this case, neither the cold or warm air is advancing. The blue arrow is an arrow and should be pointing either into or out from the page to be technically correct. A front is defined by the direction of movement of the cold, more dense air. So in this case, if neither are moving, or if both are moving at an equal speed, we get calm, beautiful clouds. Calm, no rain, nothing's being pushed up, nothing's being pushed down, just hanging out. So this is going to lead to global atmosphere. If we live in the mid-latitudes, which we do, so mid-latitudes 30 to 60 degrees lat, remember that Skagit's at 48 degrees latitude, so right between these two. We agree that the weather's always changing, and sometimes it's in the matter of hours, sometimes in days, and we also have 4 distinct seasons. Some locations on Earth have persistent weather patterns throughout the year with little to no changes between seasons. And these are going to be near the equator at 0 degrees latitude, or subtropical latitudes, 15 to 30 degrees lat, north and south. These persistent weather patterns are generated by the Hadley cells, which we talked about. Remember, those are probably the most important cells. If you remember any of the cells we talk about today, the Hadley is the most important, but you don't have to memorize that. And this is idealized global circulation. So these questions are: what weather pattern is associated with equatorial low? What is associated with subtropical high? We're going to look at that. We're going to bring this picture back. Here are the Hadley cells. So this is the equator. And remember that these air parcels, so these are technically the air parcels because they're a larger scale than regional localized masses. These parcels of air are moving, and remember, they want to go from high pressure to low pressure. Heating the lower atmosphere leads to convection and pressure differences, leading to wind, and the Coriolis effect combines to influence the vertical and horizontal movement of air. You can memorize this diagram, but I've done this one for you, and I like this one a little bit better. I added in the LP and the high P. So this is where we see, based on the circulation of air, so these are the These are the Hadley cells, these are the northernmost cells, and as these cells meet, we're going to see different pressure systems. So right at the equator, we have a low pressure system. This is where we see rising winds come up. We see warm, moist air rise, and it produces rain. So the equator gets a lot of fucking rain. It's very warm here, so we see a lot of evaporation from the ocean, which we saw in the hydrosphere module. And it's warm, and once this rises, it's going to condense, and it's going to rain. That is a low pressure system. As we move further up, so here's 30 degrees, these are our subtropical high zones here, we see cool air sinking because it's all convective, and it warms up and dries out. We see a lot of deserts here. So the Sahara is right on the subtropical zone. This is a high pressure system. Here in 60 degrees, we're at 48 degrees, so we're like here-ish. At 60 degrees latitude, we get rising winds again, and we get a low pressure system. So basically, anywhere where we see rising winds or rising circulation, we have a low pressure system. Oopsie, went too far. Anywhere where we see wind and air sink, I shouldn't say wind, anywhere where we see air sinking, we get a really high pressure system. Remember, we don't like high pressure systems. We want those high pressures to go to low pressures. But it does go opposite, which is really nice. We go low to high to low to high. And it's going to be the same moving downwards as well. I just wanted to go up. So anywhere where we see sinking winds, high pressure. Anywhere where we see rising winds, low pressure. This is just another depiction. Low pressure, high pressure, low pressure, high pressure. And why are we talking about low pressure, high pressure? Because this is going to bring us to different weather types. Calm weather. And calm weather is generated by the following conditions: a stable atmosphere, a temperature inversion, subsiding dry air associated with the subtropical high and polar high. And this calm weather can include clear air and maybe a slight breeze. Fog is considered calm, and that's generally associated with temperature inversion. Another visual to think about in this capacity is, remember when we see that snow, that layer of snow, and the sun is hitting it, and it's beautiful. We see this water vapor come up and get kind of foggy. That's because we see heat hitting cool substances. This is also why we generally see fog in the day. When we see warm temperatures hitting cooler substances, it creates fog. Weather that is generated by a warm front. So a warm front, where we see warm hitting cold and sliding up slowly because it wants to rise, is generally calm, right? It's a slow movement of an air mass going above a cold air mass. It's not a sudden thwap. We're gently rising. But clearing air after a passing cold front. So remember, cold front hits a warm front really fast, and that warm front's like, and it rises really quickly and dumps a bunch of rain. But as soon as that air is up and all of that water has condensed as precipitation, we see calm weather. Subsiding air is where we see high atmospheric pressure. Remember, we want to go from high to low. So that high pressure is moving away. We see calm weather. And desert has calm weather. Sometimes it gets windstorms, sure, but predominantly a desert, and this is the Sahara, yeah, this is the Sahara, is a very calm weather scenario. This is in the subtropical region. Fog is calm. I don't know why I have all these words in here, but calm. Calm. This is actually a good point, is that the reason this is considered calm, even though it produces rain is because it's slowly sliding over this cold front. There's actually a little wind associated with this. It's not a crazy windy scenario. So this is the typical gray wet weather, which is happening right now outside my window. No, warm front. Passing cold front. So the calm after the storm. Again, as soon as that cold front hits the warm front goes, dumps a bunch of rain. But as soon as that cold air sort of takes over and the warm air is already up in the air, we get calmness. This was probably after a cold front. I don't know why I put this. I know why I put it in here, but I didn't explain it, and I apologize. This is probably after a cold front because we see all these clouds up here, which likely indicates that a warm front was pushed upward. A bunch of rain came pummeling down onto Earth, but now we're in a calm after the storm situation. My cats are being really naughty right now, and I'm not really sure what's going on. It's nap time, you guys. You just had lunch. What's happening? I know. Let's talk heavy weather. Heavy weather and storms, so stormy weather, global atmospheric circulation and stormy weather are predominantly in tropical latitudes. This is where we see low pressure systems. I should say previous, not pervious. What are we doing? Are you coming onto my lap? Come in. Okay, I can't help you if you can't figure out your life choices here. Come here. The previous topic presentation stated that the tropical latitudes near the equator experience persistent weather patterns throughout the year with little change between seasons. This persistent weather is generated by intense heating of the lower atmosphere, leading to rising air and low air pressure. All this combines with trade winds to bring about the intertropical convergence zone, which fluctuates north and south of the equator with the seasons. So the rising air, warm air, takes a lot of water vapor with it, and as that cools as it gets further up, condensation occurs and dumps water into the ocean or into the equator. This makes for very unstable air, and it promotes the formation of very tall cumulonimbus clouds and eventually heavy rain every day of the year. Um, I love cumulonimbus clouds, and I remember this word. Hopefully, you've seen the movie Up from Disney. When the kid is like, I see cumulonimbus clouds, and then they enter a storm, and it's a whole thing. It's great. So again, I am re-showing this slide just to redepict that we have low pressure systems, and low pressure, parcels of air want to get to low pressure, but just because they want to get to low pressure doesn't mean that they're not going to dump that water, and doesn't mean that they're not going to have stormy weather. So that's sort of a thing, a takeaway. So thunderstorms. This is when we get a cold front, and it's a frontal wedging. When a cold air mass collides with warm humid air, remember the cold front hitting the warm air, and the warm air is going to go, and it forces that warm air upward. Oh my God. The rising warm air takes water vapor with it. As the air cools, condensation occurs, and water vapor releases latent heat to warm the air. And because all of these processes are occurring, the air becomes really unstable. This happens along mountain ranges a lot. And so as the rising air is warmer and the air, so the mountain range is similar to the rain shadow effect. So as long as the rising air is warmer than the air it is rising through, it will continue to rise and contribute to atmospheric instability and stormy weather. Back to this depiction again. So our warm air goes upward, and we see unstable air occur, and we get a downdraft, and we get heavy rain and sometimes hail, and we get thunder and lightning. Oh, this is the depiction of an anvil cloud as well. So we see thunderstorms occur when we get really big cold fronts hitting massive parcels of warm air. So this is a dramatic take on a cold front, basically. Tornadoes are kind of crazy too, in the sense that they get these low pressure systems, warm air parcels that rise, and then the cold air begins to want to sink. And it's a really cool process where you get low pressure and a high pressure system sort of colliding at the same time, and it causes the wind around it to start to spin and circulate, and you get counterclockwise movement, particularly in the northern hemisphere where we see tornadoes. And so tornadoes are considered obviously a stormy weather event where we get two parcels of air that hit at high wind speeds, and they'll spin into a funnel. But let's talk about the type of heavy, oh, I talk cyclones and hurricanes first. Okay. And I do want to talk cyclones and hurricanes because I think they're important. So they're considered the most violent storms on Earth because of the speed at which they get and the spatial, how big they get, I guess, essentially. So they tend to form near the equator, and they'll form over warm ocean waters. The term hurricane is used for large storms that form over the Atlantic Ocean or the Eastern Pacific. We're a part of the Eastern Pacific here on Washington State. However, the general scientific term for these storms, wherever they occur, is typically a cyclone. So when you hear cyclone and you hear hurricane, this always gets me too. They mean the same thing, basically. It's just entirely dependent upon geographic situation. But other names that they're given are typhoons, tropical cyclones, severe cyclonic storms, but they all sort of amass the same meaning in these hurricanes. Geographically, here are hurricanes here. So Hawaii might get hurricanes. Cyclones tend to happen down here in Southeast Africa. Yep, Southeast Africa or Australia. And typhoons, same premise, but they tend to happen over here. And in fact, a typhoon generally hits India regularly, and they call this monsoon season. So these tropical cyclones or hurricanes or typhoons, yeah, typhoons, are like engines and they require warm, moist air as fuel. So the first ingredient needed is warm ocean water, which is why they begin over equatorial regions. This is why tropical cyclones form only in tropical regions, where ocean is at least 80 degrees Fahrenheit at the least top or at the highest 50 meters below the surface. Hawaii. If you've ever been to Hawaii, those waters are toasty. The second ingredient, as you can imagine, for these cyclones are wind. So not only do you need warm air above equatorial regions, you need a lot of wind. And that wind blowing westward across the Atlantic from Africa provides the necessary ingredient. As the wind passes over the ocean surface, more water will evaporate as part of this process, and it will rise. As it rises, the water vapor cools and it condenses into large water droplets and forms these giant cumulonimbus clouds. So the stages of these storms are in four stages. There are four. Meteorologists have divided these developments into four stages: a tropical disturbance, tropical depression, tropical storm, and a full-fledged tropical cyclone. And it all has to do with speed. How fast have these uh, cyclones and hurricanes reach? So when we hear, oh, this cyclone's at stage 1 or stage 2 or stage 4 or stage 5, it all has to do with how fast and how large these tropical storms have reached. So when the wind speed reaches 39 miles per hour, the tropical depression, oh my gosh, tropical depression becomes a storm. This is also when the storm gets a name. There has been a Hurricane Emily before. Fun fact. The winds will blow faster and begin twisting and turning around the eye or the calm center of the storm. So I also want to make it clear, but these get really, really big, and they also follow the Coriolis effect to a lot of degrees. Warm water will evaporate, the moisture rises, and it starts just by creating thunderstorms. So we get this fast-moving wind and these very dramatic low and high pressure systems that form thunderstorms. But as this entity grows larger, the winds begin to spiral upward and outward. A low pressure system forms over the ocean surface, meaning that clouds are going to start to form in the upper atmosphere, and this warm air is going to condense. The entire storm system starts to spin, counterclockwise or clockwise, depending on the hemisphere. That's the Coriolis effect. When the winds rotate to 74 miles per hour, so that's not super fast. Category 1. Category 1 hurricane is born, and a Category 1 is the lowest category hurricane. When the storm passes over the land, the supply of moisture from the ocean and the heat from the ocean and that atmosphere is cut off, and the storm gradually dissipates. But we're not done with that. So when wind speeds reach 74 miles an hour, the storm is officially a hurricane. Category 1. This storm is at least 50,000 feet high and 125 miles across. That's a lot of miles, you guys. The eye is around 5 to 30 miles wide. And the trade winds that move from east to west are going to push that hurricane towards the west or towards the coast, towards the Caribbean, the Gulf of America, or the southeastern coast of the US, Florida, South Carolina, North Carolina. The winds and the low air pressure can also cause a huge mound of ocean water to pile up near the eye of the hurricane in a gyre. Remember, we were talking about gyres and the hydrosphere and these bulges. This happens when you have a spinning entity of air moving faster than 74 miles an hour, pulls some of that water up into a gyre. This is a storm surge. And as these hurricanes move over the land and it loses the moisture from the ocean and it loses the heat, it's also got to put all of that rain and wind somewhere. So it just dumps. So this is a storm surge from a hurricane. I don't want to say it's similar to a tsunami because they're very, very different processes. But they are similar in that all of a sudden you get this wall of water coming at you. So this happened in Hurricane Katrina. I don't know, this might have been from Katrina actually. And this is also why the levees broke in Katrina because the levees, so basically, New Orleans is below sea level. And so they built these levees along the shoreline to make sure that the ocean didn't fill New Orleans. But during Katrina, Hurricane Katrina, this gyre came and busted these levees and basically flooded all of New Orleans because it's below sea level. And because this gyre was huge, these storm surges came and just tackled through all of these seawalls that they had tried to build. It was really sad. So those are hurricanes. And I did want to talk briefly about those because I think that they're really important to talk about. We don't necessarily see them here in the Pacific Northwest. But one of the things that I have been reading about is that we are anticipating more and more sea storms and ocean storms, and we live on the Salish Sea. And there was a fear, now this is me fear mongering, and I do apologize because there's no evidence yet, that we might begin to see events like cyclones more commonly along the West Coast. But our biggest, at least on the West Coast, our biggest weather event driven by this atmospheric process are called atmospheric rivers. Um, and if you are not familiar with atmospheric rivers, you're about to be. But maybe you've heard this term, and you probably have heard it recently because the atmospheric river was what drove the flooding events of December 2025. It's also called the Pineapple Express because an atmospheric river starts in a tropical or equatorial area. And here we have it starting in Hawaii. And the winds and this high precipitation, or sorry, um, the, I think I explained it better. Yeah, I shouldn't just spew it. I wrote it all down. So they're long, narrow bands of moisture that move like rivers in the sky. They transport water vapor from the tropics, like Hawaii, towards the poles. All right, here's where I was trying to get at, but it's better when I read it instead of just trying to pull it from my memory. So they form when a large low pressure system, remember low pressure systems produce a lot of rain, moves over a warm body of water like the Pacific Ocean. And as it moves, it continues to pick up more and more moisture. As the low pressure system moves over land, that moisture is then released as precipitation. Remember the rain shadow effect as well. So the event in December 2025 occurred from 7,000 miles away from the Philippines, actually. We got an atmospheric river from the Philippines, which is across the Pacific Ocean. It came from a distance. This entire river moved across the entirety of the Pacific Ocean until it hit Washington. Lucky us. So river floods were ongoing December 11th, with the Skagit and Snohomish River seeing record or near record floods on December 11th. Western Washington received more than 10 inches of rain over a 72-hour period in the morning. That's a lot of rain, you guys. That is this much rain in 3 days. This much rain. SeaTac Airport set a daily a daily rainfall record on December 10th with 1.6 inches in a day. We receive on average less than I think it's like 0.2 inches per day on average. And obviously that takes into account our winter months and that takes into account our summer months when we maybe don't see any rain. 1.6 inches in one day is like that much. That's a lot. So this is just another depiction of an atmospheric river or Pineapple Express. So this is me reiterating the rain shadow effect. And this is in California, but this is exactly what happened in Washington. We get this atmospheric river, and when it hits high topography, like mountains, it has to release this water. The water vapor cools as it gets higher in elevation, it condenses, and then it drops as water. And this is why the western slopes of Washington State got so much rain in December of 2025. So this is also at least three Lake Washington's worth of water fell during the atmospheric river during December 2025. This is a lot of rain. Um, okay, I have something I want to say, but I'm going to say it after the next topic because this is what's going to drive what I say next. Let's talk El Nino and La Nina because they're related, and we're going to come back. Um, I assume that you have heard the terms El Nino and La Nina, El Nino and La Nina, and I am assuming that you have contributed them to atmospheric and climatic events. And if you have not, let me describe them for you. Um, well, maybe I don't define them. I apologize. So it was these terms were described, gosh, I want to say in like the 70s from South America. And it started with fishermen actually, because fishermen were noting years that there were fewer fish. Um, and those years they would call El Niños, the boy. Regular years, but dramatic years where they did get fish, but maybe excess fish, they called La Niñas. So this all sort of derived from fishermen who noted how fish behavior and patterns were affected by climatic changes. And this is because in a regular normal condition, we call this the Walker cell. Okay, so this is the Walker cell. It's similar to the Hadley cell, but because we're in higher equatorial regions, we'll call it the Walker cell. And this is when we see trade winds pushing warm, humid air to the western Pacific. This is normal. This is what happens regularly, or it should be happening regularly. We see winds pushing warm, humid air to western Pacific, which would be towards Japan. Because we're going from high pressure. Remember, if we're in high pressure, we want to go to low pressure. So we see these winds going from high to low. Once it reaches the western tropical Pacific, it rises. And then it expands and it cools. So we have some convection going on here. This is the circulation going on. We see heavy rainfall because of this over in this area here. Now, the other thing to note, and the reason I put this topic in these slides and not the oceanographic slides, is that we see upwelling from bottom waters come up to the surface. And remember, this upwelling, where we see colder water rise to the surface, this upwelling brings nutrients. And so these fishermen, they see fish normally in the summertime when these nutrients are rising and there's food for other organisms, and the fish can come feed on these organisms or on the nutrients, right? So these are normal conditions. Oh, this is the same thing. Normal conditions. We just talked about this, so I'm going to skip this slide. Now we have two anomalous phases. We have an El Nino. And an El Nino occurs when easterly trades relax and this warm pool shifts closer to the United States. It shifts east. But remember, we're over the Pacific Ocean. So when we're on the Pacific Ocean and we're shifting east, we're seeing these winds shift closer to the US. And we see two cells form. So all of this water, instead of heavy rainfall over the Japan area and the Western Pacific, we see this rain now in the central area of the Pacific Ocean. And what this does is it actually changes what we call the thermocline, or the layers in the ocean, and there's no upwelling that occurs along the South American margin here. So this is where the fishermen were noting we don't see fish in these years. And that's because there was no upwelling here. This is an El Nino. This is low biological productivity. Now, a La Nina, all I'm going to say about a La Nina is it's the same as normal conditions, but more dramatic. We see more upwelling. We see more winds pushing this precipitation cloud even further. So what we see in these conditions In an El Nino condition is we see hotter temperatures through the western United States. We also tend to see, um, and this is the Southwest. We also, this is our subtropical jet. So this is rain. We don't see rain in Washington. Here's Washington. When we get an El Nino, we get a lot. The poor California gets a lot. Mexico gets a lot of rain. The Southwest United States gets really, really hot temperatures. Um, but we don't see rain. When we get a La Nina, this is when we do see rain, and we see a lot of rain. So here's that subtropical jet, and it's hitting Washington. So this year, and you're going to do a little bit of reading on this. Oh, I don't know if you do it for this module or the climate module. Regardless, you're going to do reading for it this term about how this year was weirdly anomalous in that we started in La Nina conditions, which is why we got the atmospheric river December 2025 and we just dumped rain. We had weird La Nina conditions. We have now changed into El Nino conditions. This never happens. Every year we're either one or the other or normal conditions. What we're finding is that because of climate change, we're getting significantly more La Nina conditions or El Nino conditions more frequently. And this is one of the first years that we've seen where they've switched in the middle of the year. This doesn't happen. It's unheard of. So we started with La Nina in the winter. We had a La Nina winter, and now we're seeing El Nino conditions where everything's about to be really dry, really hot. And in fact, in one of the articles you'll read in this term, again, I don't remember which module I have it for, they're predicting some of the hottest temperatures in the summer because we've switched from La Nina to El Nino. So the reason I wanted to talk about this is because of climate change, we're seeing more El Nino conditions and La Nina conditions more frequently than we have before. And now we're starting to see them swap in the middle of the year, meaning that our atmospheric rivers are going to get significantly worse year by year. And the floods that we saw in December of 2025, uh, if you were here and you are familiar with it, they were like, oh, this is a 100-year flood, meaning that these floods only ever occur once every 100 years. But as we see this climate shifting and we see more common El Nino La Nina events regularly, we are going to see more atmospheric rivers, meaning we're going to have more flooding events. So when you're like, how does atmosphere relate to geology? Why did we go through this whole premise? This. Because atmospheric rivers directly affect geologic processes that occur, especially in Skagit County. They directly affect our flooding scenarios, our river systems, our stream systems, all of which are incredibly dynamic as they already are. But the more that we change our weather events and our climate systems, the more we're going to see these geological processes occur. And furthermore, I've mentioned in both geosphere and hydrosphere that our rainwater is acidic, right? It is slightly acidic because it is reacting with the carbon dioxide in our atmosphere. The more atmospheric rivers we get, the more precipitation we get, the more weathering and erosion we're going to see in part because of these climatic events. It's all related. So I didn't just throw atmosphere and weather in here for funsies. It's because it's all related and you have to know all of these concepts to understand how it all reacts and interacts with geology. All right. Oh, here. This is the article, one of the articles I think I have you read. So El Nino forms and is expected to strengthen. This was from June 11th, so last month, 2026. We are expecting and we have modeled prolonged periods of above average temperatures in the equatorial Pacific and expected to peak this winter. So this also goes into how not only are we going to have a hot summer, prepare for a hot summer, get your air conditioner out now. But we're also probably going to have a mild winter in that we're likely going to stop seeing snow regularly, and it'll be a treat to see snow moving forward in Washington, which maybe is great for you if you don't love snow, but this also plays into the snowpack on the mountains, which we'll continue to talk about for the rest of this class. Here is the modeled diagram of the El Nino. This isn't modeled, I apologize. This is actual satellite imagery, infrared imagery. I remember reading about this. Um, these are just usual impacts. So we're going to see stronger winds, stormier weather in the southern US, high tide flooding in parts of the US, especially on the West Coast, changes in migration of fish and other oceanic organisms with warm water moving north. Y'all, we have found salmon species in the Arctic that aren't normally up there because of climate change. We have seen a more formations of harmful algal blooms. We're going to come back and talk harmful algal blooms when we get to the anthroposphere. I think they're really interesting, but I'm not going to dive into what they are now. And here in Washington State, expect to see higher temperatures, drier weather conditions. So today's a bit of an anomaly because where the heck is this rain coming from? Not mad. We need the rain. Um, but it is a weird anomaly. We got a cold front, is what happened. It's a gentle cold front that came and is sliding along a warm front and saying, let me just rain gently. All right. Next module is biosphere, which is my favorite, and that will start with just one video. So this was your last module with 2 videos. You are welcome. And I'll see you in a week.